Okay, so welcome everyone to one more edition of the Brazilian Algebraic Geometry Seminar. And this week it's a pleasure to introduce Roberto Villaflor from IMPA, and he will talk about constructing algebraic cycles on hypersurfaces, an explicit approach to Hodge conjecture. Go
Well,
ahead, Roberto.
thank you. Thank you for the invitation. Thank you all for attending to this seminar. Well, what I want to talk to you about today is a circle of ideas I've been thinking about that have been appearing in my latest work. It's not my intention to prove Hodge conjecture or something like that. So I just want to give you a big overview of what I've been thinking and how these ideas can be used to try to approach to an explicit version of Hodge conjecture that, well, nobody has tried to do this before. So I think this is interesting. So let me start by introducing the Hodge conjecture in the case of hypersurfaces. So we will consider X a smooth hypersurface of the projective space of degree d and dimension n. So since this is a smooth projective variety, we know that the RAM homology groups have a Hodge decomposition that is something like this. And in the case of a hypersurface, we know that the Hodge, that the homology groups are almost all trivial, except by the middle, right? So if we assume that the hypersurface is of even dimension, we have a non-trivial homology group of even degree exactly in the middle part, which has a Hodge decomposition like this. And all these subspaces, they are in principle non-trivial. So inside this vector space, we have a lattice that is the lattice of singular homology. And if we tensor it like Q, we can have also a rational subvector space of this complex vector space given by the rational class. Okay, these are like the rational points of this vector space. So we say that a class is Hodge if it lies exactly in the intersection of the middle part of the Hodge decomposition with the rational class, right? So in concrete terms, we can see this by the following relation. So in terms of integrals, we can express that a class is in the middle part of the Hodge decomposition in this way. These periods must be zero for every form not in the middle part of the Hodge decomposition. And the rationality can also be seen in terms of period, right, in the following way. So if we take the period over a rational cycle, it must be a rational number. Okay, so this expresses what a Hodge cycle is in terms of integral. Okay, so examples of Hodge cycles are algebraic cycles. An algebraic cycle can be constructed, for instance, taking a closed subvariety of dimension n/2. Well, since here, well, during all the talk, I'm just talking about considering the smooth hypersurface, so I'm not interested in the other degrees of the RAM homology groups, just in the middle one. So we consider an n/2 dimension subvariety. It determines an algebraic cycle, and this algebraic cycle determines a rational class in the homology group. And it's given by the following relation in terms of integrals. So you can express it like this: the class of the algebraic cycle given by this relation. And when you write it like this, it's easy to see that this class is in fact in the middle part of the Hodge decomposition, and so it is a Hodge cycle. So every algebraic cycle is a Hodge cycle. And what the Hodge conjecture claims is the converse, right? That all Hodge cycles are algebraic cycles in this sense. So a form is algebraic. This means that it is a rational combination of classes of algebraic cycles. If and only if it is Hodge, right? So it can be expressed in this form. This is the Hodge conjecture. Okay, so this is the conjecture we are interested in. This is an extremely important conjecture. And okay, let's continue. So now I want to go back to the title of the talk, constructing algebraic cycles on hypersurface. So let's first look at a very naive example. So consider the Fermat variety. The Fermat variety is the simplest equation that you can imagine. And I ask you to find algebraic cycles inside it, right? So how do we do it? So there is a simple way to construct algebraic cycles in the Fermat variety. That is in the following way. We can aggregate the variables in groups of two monomials, and then we can factor them out as a product of linear polynomials. And after we have written the equation in this form, we just need to choose some of the factors here, put it in one polynomial and the rest in other polynomial. So we obtain an expression like this, where all these polynomials are products of linear polynomials. And so we can construct the subvariety C given by choosing some of these polynomials and put them equal to 0. This will obviously be an algebraic cycle inside Fermat, and furthermore, it will be a union of linear subvarieties, right? So in this way, we can produce a lot of algebraic cycles inside it. So the question is, do they generate the whole space of Hodge cycles or the space of algebraic cycles? So there is a theorem, a classical theorem due to Rahn and Shioda, that characterize the Fermat varieties with this property. So they said that the Fermat varieties where the linear cycles generate all the Hodge cycles are exactly the following one. In degree 4, degree prime, or with degree relatively prime to n+1 factorial. These are all. So the answer to this question is, well, not always. Not always the linear cycles are enough to generate all the Hodge cycles or even all the linear or the algebraic cycles. So for instance, we can take the Fermat sextic surface. In this case, the Picard number is 86, and the sublattice generated by linear cycles has rank 52. So we need to construct more cycles. So, well, let's take the equation. So in a very simple terms, what we are looking for is for new ways of factoring out this equation, right? So there is we can try to be more creative and do the following factorization. So consider now this expression. These two polynomials can be factored in the following way. So this is a very, very simple factorization if you remember your days in high school. And from this, we can produce a new algebraic cycle, just considering this polynomial and this one. We produce this cycle, and this is called an Aoki-Shioda cycle. These kind of cycles, in fact, are new algebraic cycles. They are complete intersections, but they are not generated by linear cycles. And in fact, if we consider the rank that they generate together with the linear cycles, we will see that in this case of the sextic Fermat surface, we obtain the whole Picard right? Okay, so this answers this problem in this particular case, this very particular case. So what happens if we go further to other examples? For instance, the surface of degree 12. In this case, we will have that the amount of cycles that we need beside the linear cycles is much bigger. Okay, so in this case, in fact, it will happen that the Aoki-Chiyoda cycles, or a sort of generalization of Aoki-Chiyoda cycles, are not enough to produce all algebraic cycles. Okay, so in general, how can we get more cycles, more algebraic cycles? So, well, we don't want to rely on our creativity to find new factorizations of this very simple equation, but we want to produce a systematic approach to try to produce new algebraic sets. So we will try to do it in terms of the Hodge conjecture. So this leads us to the first question, which is how can we construct more Hodge cycles on it? So, and the second question is the main question of this talk, is how can we construct equations from a given Hodge cycle? Okay, so clearly question 2 seems to be the hardest question because it is in the core of Hodge conjecture. I mean, it's Hodge conjecture, but an explicit Hodge conjecture, right? We want to construct equations. And what I want to try to express to you in this talk is that if we are able to construct Hodge cycles in a very nice way, in a good way, question 2 becomes more treatable. Okay, so as I said before, I won't talk about any concrete results. I will just give ideas and examples, and I want to set up the questions which will enable us to go further in this direction. Okay. So, what do I mean by a Hodge cycle written in a nice way? So let me recall Griffiths' basis theorem. Again, this is our context, smooth hypersurface of even dimension. Griffiths' basis says the following. So we want to construct a basis for the ramp homology of X, the middle group of the ramp homology. So it says construct the forms given in the following format. They will be residues of meromorphic forms which are vanishing along a certain polynomial of a certain degree, and they have pole of order n over 2 plus 1 along the hypersurface. Okay, Griffiths' theorem says that whenever you consider this format, it will land in the middle part of the Hodge filtration of it. Right, the middle part of the Hodge filtration is exactly this part of the Hodge decomposition. It says more. It says that the image of this map is in fact the primitive part of the middle part of the Hodge filtration. The primitive part is exactly the same Hodge filtration, but in the middle part of the Hodge decomposition, we're considering those forms which are orthogonal to the polarization, which is the class coming from the projective space. Okay, so this is a hypersurface of the previous filtration and hyperplane, I mean, and when we look at the image of this map in the following quotient, the quotient by the next part of the Hodge filtration, the kernel of this map is exactly the Jacobian ideal of F, right? So the polynomials that are going to this part of the filtration are exactly those polynomials which belong to the Jacobian ideal. And so we have a correspondence between an homogeneous degree sigma part of the Jacobian ring and the primitive part of the middle part of the Hodge decomposition of X. Okay, in this sense. So I will say that an n over 2 class has Griffiths form omega p if whenever I look to lambda inside this quotient, it is equal to omega p. So in other words, the primitive part of lambda is the middle part of omega p. Okay, so by what I said, this p, this omega p, is unique in the Jacobian ring. Okay, so what I want to express in this talk is that whenever you know the Griffiths form, and by this I mean you know this polynomial, you have a lot of information about lambda, right? For instance, we can compute easily the periods of lambda in terms of this polynomial. This is the following proposition that is a simple proposition, which says that all the periods can be computed whenever we have two forms in terms of Griffiths basis in the following simple way. The period, or the information, the non-trivial information of the period, is given here by this relation. So it is a number which depends on the coefficients of the polynomial t, the polynomial q, and the polynomial f. Okay. So, well, for me, this will be a Hodge cycle written in a nice way. So, in order to advance to the second question that I stated before, so to answer the question of how can we obtain equations from a Hodge cycle written in Griffiths form, I have to introduce first a very nice kind of ideas, which are the Artin-Gorenstein ideas. So let me recall what they are. I will say that an homogeneous ideal is Artin-Gorenstein of tuple sigma if it satisfies, if the quotient ring satisfies the following relation. So what you have to have in mind is that this ring is a sort of a cohomology ring of a compact orientable manifold. So in the following sense, so it has a top homology, right, which is of dimension 1. Above the top homology, everything vanishes, and under the top homology, you have a Poincaré duality, right? This kind of rings are Artin-Gorenstein rings of tuple sigma. The tuple is the sort of dimension in this case. Okay. So how can we produce examples of Artin-Gorenstein ideals? We have this nice theorem of Macaulay, which says that whenever you take an ideal which is a complete intersection given by equations, then the ideal is Artin-Gorenstein of this tuple, the sum of the degrees minus 1. So this is a very simple way to produce Artin-Gorenstein ideals, and these are in fact not all kinds of Artin-Gorenstein ideals. This is a very special kind of Artin-Gorenstein ideal, which are complete intersections. And well, these are some examples of this kind of ideals. The Jacobian ideal of a smooth hypersurface is one of these examples. It has tuple this number, d minus 2 times n plus 2. So here I am in the same context always. X is a smooth hypersurface degree d, dimension n even. And other way to produce an ideal which is complete intersection is to consider now a complete intersection subvariety inside the smooth hypersurface and take the ideal generated by all these equations. This will be also a complete intersection by Macaulay's theorem. It will be Artin-Gorenstein, and it will have tuple this number, which is the middle of the previous tuple of the Jacobian idea. Okay, so this is a way to produce Artin-Gorenstein ideals. And now what I want to do is to associate an Artin-Gorenstein ideal to every Hodge cycle. Okay, so this will be the key to obtain equations from a Hodge cycle or a homology class. So again, this is our context. So the definition is the following. Consider any n over 2 n over 2 class such that is non-zero in primitive homology. And we will associate the following Artin-Gorenstein ideal of circle d minus 2 times n over 2 plus 1. Again, this is the middle, is the half of the circle of the Jacobian ideal. And we will define it in each homogeneous piece in the following way. So consider the homogeneous polynomial such that these integrals are 0 for every polynomial t. Here, omega st is again an element of Griffiths basis associated to the polynomial s times t. So this definition at first might seem very artificial, very strange, but it's not artificial at all. In fact, it comes motivated from the infinitesimal variations of Hodge structures and the study of the Hodge loci. And I don't want to go deeper in this definition, but the point is that we can define it without all these assumptions on the, without knowing anything about the infinitesimal variations of Hodge structures. And furthermore, whenever we know the Griffiths form of the homological class lambda, we can compute this ideal in a very simple way. So this is done in the following way. So we will have that by definition, this is equal to this. Now, if we remember the proposition about the periods of forms written in Griffith form, we will see that this is 0 if and only if this product of polynomials is 0 in the Jacobian ring, right? And now, since the Jacobian ideal is Artin-Gorenstein, we know that the product in the Jacobian ring is a perfectarian. So this means that this is equal to this, which is exactly the quotient ideal. So whenever we know this polynomial p, so whenever we know how to write lambda in Griffith form, we can compute easily, or we have a nice description of this associated Artin-Gorenstein ideal in terms of this polynomial p and the Jacobian ideal. Okay. So what I'm trying to tell you is that this we can construct this ideal for every Hodge cycle, and furthermore, whenever we know its Griffith form, we can compute it. This ideal satisfies the following relation. So it is not characterizing the homological class of lambda, but it is characterizing it in the primitive homology modulo the action of C star, right? So in particular, it is detecting the algebraicity of lambda, right? Because the polarization is algebraic, it's an algebraic class. Okay. Well, what I want to tell you is that this definition, this ideal, was not introduced by me. The first person to introduce it was Claire Voisin and Mark Green, but they use it as part of their argument, and well, they never gave it a name, and it has been used by several mathematicians after them. But up to the day, I believe that nobody has put a name to it and paid too much attention to it. So now I want to argument how can we construct the equations from a Hodge cycle written in this nice way, in terms of this Griffith form. So let's consider some examples. The first example will be examples of algebraic cycles, which are supported in some simple algebraic cycles. So if we consider a complete intersection inside X, a smooth hypersurface, and we take lambda to be the homological class of C, right? We want to reconstruct in some way the equations of C just by looking at the class lambda. So what I did is to compute the Griffith form of such an algebraic cycle. and it will be given by this polynomial. It is the determinant of the Jacobian matrix of this vector, where these polynomials again appear in the factorization of S. And so in particular, we can compute the ideal associated, the Artin-Gorenstein ideal associated to lambda. And it will be exactly this ideal. Again. So we see that the equations defining this algebraic cycle appear as generators of this ideal. In fact, we obtain more than this. We obtain generators of other algebraic cycles, which are also representing lambda in this sense, right? Well, in primitive cohomology. So for instance, we can take C prime defined by G1 instead of F1, and in primitive cohomology, it will be equal to minus C, right? Because the sum will be given by F times G, F1 times G1 equal to 0, and this will be an hyperplane section. So, so in resume, this is the setting for the case where lambda is supported in just one complete intersection cycle. We will get the equations just looking at this ideal, and as I said before, this ideal can be computed if we know the Griffiths form of lambda, or we have a way to compute it. So let's consider other examples. So consider now a prime variety, but which is not a complete intersection. For instance, twisted cubic. The twisted cubic, well, it is given by the following minors of this matrix. So there are the upper 2 times 2 minors of this matrix M, and any surface containing it will be the determinant of some of such a matrix like this. So again, we can consider the cohomological class of the twisted cubic and compute the associated Artin-Gorenstein ideal. And what we are able to show is that this Artin-Gorenstein ideal is in fact the ideal generated by all the 2 times 2 minors of the matrix M, not just the ones defining the twisted cubic, but all. And in fact, what we see is that again, the equations of the twisted cubic are appearing as generators in low degree of this ideal. So this is what happens in this case. So in general, what is happening? So in general, well, we don't know, but we know is the following. If you consider any Hodge cycle, which is non-zero in primitive cohomology, and we assume that there is a reduced variety that is supporting it in the following sense, right? Such that lambda, the primitive part of lambda, is a multiple in primitive cohomology of the class of Z, then the equations of this subvariety must appear somewhere in this ideal. In fact, we will have that the ideal generated by C is contained in this associated Artin-Gorenstein ideal, and this is a very simple observation. You can prove it directly from the definition of this ideal. So there is the question. So is it true in general that we can generate, at least in a small degree, the Artin-Gorenstein ideal associated to the class lambda, just by taking the ideals, the equations of all algebraic cycles supporting it in this sense for some degree, right? So this is what I said. This is what I mean. So whenever we look at least for degrees less or equal than the least degree where the ideal of the supporting algebraic cycle is generated, can we obtain all the possible equations defining these cycles which are supporting this class, looking at this ideal? Well, this is something that I don't know, but something that is happening in the examples that I am considering. So this is the kind of argument that I have in order to construct equations of a cycle given the Griffiths form of the algebraic cycle, right? We have to look to this ideal, and this ideal can be computed. Okay, so what we expect is that the equations must appear in the small degree generators of the idea. So now, how can we detect new algebraic cycles? Okay, so I have told you that whenever we write the algebraic cycle in this nice way, we have a sort of a magic trick to obtain some equations that can be defining the support of the algebraic cycle. So how can we know if we are taking a class written in Griffiths form that we know that it's Hodge, but we want to know if this class is supporting a new algebraic cycle, an algebraic cycle that we haven't, we don't know yet. So let me explain what happens in some examples. So now consider two linear cycles inside a smooth hypersurface. For instance, here you can consider Fermat. So we will look at all the possible combinations of these two linear cycles, combinations with a positive integral values. So when we look at the Hilbert function of this combination in terms of A and B, it will happen that the Hilbert function in general will behave, will have a general behavior that is independent of the values of A and B in general, right? Obviously, the behavior will change if we take, for instance, A equal to 0 or B equal to 0, because the class will be supporting just one cycle, the linear cycle, right? So what will happen is the following. The Hilbert function will be, in fact, the Hilbert function of the intersection of the two ideals for some degrees, right? And the relation of this relation is governed by the size of the intersection of the two linear cycles. But this is what will happen in general when you take a general combination, but there will be some other combinations, some special combinations, where the behavior of the Hilbert function of this idea will be different. It will be jumping in some special combinations, and these special combinations will be detecting the presence of a different of an algebraic cycle of different nature, which is homologous to this combination in the primitive homology. Right. So, for instance, this will happen when you take A equal to B, and you take that the intersection is too big, right? It's n over 2 minus 1. In this case, you will land in the complete intersection case of type 1, 1, 1, 2. And so the Hilbert function of this ideal in degree B, it will be jumping because of the fact that this complete intersection, in fact, has a bigger deformation space than just deforming each of the two linear cycles independently. So what I'm trying to say is that whenever you take two prime cycles and you start to combine them, the special combinations which are being homologous to some algebraic cycle of a different nature will be detected by some of these Hilbert functions, some degree of the Hilbert function of this idea, right? We will detect a jump somewhere. Okay, so in general, what we expect is the following. So we take a genetic combination of prime cycles, which is effective, I mean a positive combination. The Hilbert function will be independent of the combination. It will be also related to the Hilbert function of this intersection, and this relation will be governed by some numerical condition on the degree and the cycle, except for some special cases which will have a bigger deformation space, right? So in this way, we can try to detect new algebraic cycles. So what we do is the following: consider a Hodge cycle lambda, which in the best possible way, we know that which is its Griffiths form, for instance, and we take this class and it's not generated by a family of known algebraic cycles. For instance, we can assume that these are the linear cycles in Fermat, or maybe the linear cycles and the Aoki-Shioda cycles, and we're looking for a new algebraic cycle, right? So we don't know how to do this, but we are able to produce a Hodge class in Griffiths form, which is not generated by them, and we want to detect the algebraic cycle that it's supporting. So if we have a way to know that this cycle is effective, in the sense that it is a positive combination of algebraic cycles, what we might have is the following, right? The class lambda in primitive cohomology must be equal to something like this: a positive combination of the known algebraic cycle plus the class of a new algebraic cycle, right? Which might be non-reduced. So when we start looking at the Hilbert function of combinations of this type, we are able to compute it because, well, for instance, we know in the case of Fermat, right? If these algebraic cycles are all known, and by known I mean we know their polynomials in Griffiths form, we also know the polynomial in Griffiths form of lambda, so we can compute all the polynomials in Griffiths form of these combinations, and so we can compute the Hilbert, the associated ideals, the associated Artin-Gorenstein ideals to all these combinations, and we can compute the Hilbert function. And so we will, whenever we get their correct combination, which will be effective, the Hilbert function must jump at some degree. So this is a way to try to detect the presence of this new cycle W, right? And so with this, in this way, we will be able to detect the possible cycle, and then just looking at the generators, we should be able to obtain the equations defining it. So we will be able to produce a probably new algebraic cycle. So the question is how to know if a Hodge cycle is effective, or even better, prime, or well, this is something that I don't know how to answer, but in the particular case where it is a prime cycle supported in a complete intersection cycle, I have some results. I have done some counts, which have given me the following conjecture. Can we characterize the complete intersection cycles just by this condition? So in my latest work, I have proved that under certain conditions, this condition implies that the cycle lambda is supported in a complete intersection. So as you see, this kind of relation is the good relation we are looking for, because it is just depending on the homological class lambda, and I mean this depends just on the associated ideal, right? So we can check this kind of relation in this particular case, right? So well, now I have given to you most of the ideas that I've been thinking about. So, so what's next? So I have explained to you that whenever I know whenever I have constructed a Hodge cycle in its Griffiths form, I can try to use all this machinery to try to find new algebraic cycles explicitly. But I haven't told you how can I produce this lambda or the Hodge, or the Griffiths form of a Hodge cycle lambda. So this is the next step. How can we construct a Hodge cycle given in Griffiths form? So the simplest idea that we can try is the following. We can consider just a polynomial and look at its Griffiths form. So it is given in Griffiths form by 3, but and we ask ourselves which conditions on P guarantee that this form is a rational class. So if we recall the proposition about periods, we will see that this relation is giving us, whenever we know the Griffith form of a rational class, omega q, this relation will give us a lot of constraints in the coefficients of the polynomial p in order to guarantee that omega p will have rational periods, right? And so it will be a rational class. So, but the point is, how can we produce again, as you see, the problem is circular, right? We are trying to prove that a class is rational by using the Griffiths form of a rational class. So this is not taking us very far, but the point is that there are some special rational classes where I can compute the Griffiths form. As I explained you before, I gave you an example, right? The example of the complete intersection cycle. So whenever I have an algebraic cycle, for instance, this algebraic cycle is coming from geometry, right? It's not just a topological thing. So we can try to compute this Griffith form of an algebraic cycle, and the more algebraic cycles we have, the more restrictions we will get by these relations, right? In the coefficients of P, in order to construct a Hodge cycle, right? So this is the conclusion. So the more Griffith form that we are able to compute corresponding to algebraic cycles, the more restrictions we will get in the coefficients of P. But unfortunately, this approach is not good as well as it was expectable, because in this way we're just looking at the period at Hodge cycles, right, or at algebraic cycles. But we need to know, in order to guarantee that a class is rational, we need to look at all the periods over the whole homology group, whole rational homology cycles, right? And so, well, I have produced examples where these conditions are not enough for Fermat of degree 3, 4, and 6. And so again, this question is not trivial at all, and we can try to tackle it in a different way. We just, instead of looking at the periods just in homological terms, we can look at it in terms of integrals over the homological side, over a basis. For instance, we can fix a known hypersurface like Fermat, and produce an explicit basis of the homology group, singular homology group, right? And this is possible in Fermat using these fun cycles, or also called vanishing cycles, and we can compute the periods. But again, these periods, the periods that we can compute are exactly the periods of the form omega p. But what we want to compute are the periods of lambda, right? And lambda is just given by the middle part of the form omega p. So what we need to do is to answer the following question. How can we know if a form in Griffiths basis lies exactly in the middle part of the Hodge decomposition? Okay. So we don't just want one representative of this omega p in Griffith form, but we want the right one. We want the one that is lying exactly in the middle part. So in other words, given the Griffith form, can we find another polynomial such that we are in some way projecting it to the middle part of the Hodge decomposition, right? So again, this is something that I believe nobody has done before, and it's going in the direction of finding a sort of algebraic Hodge decomposition in the case of hypersurface, but it's not exactly that. But well, I don't know if I believe this is possible to be done, at least in some particular examples. But again, this is something that has to be answered in order to try to answer the previous question in terms of integrals, in terms of computing periods in a basis of the singular homology group. Okay, so in the last slide, I just want to treat the following question. So the previous slide was about how to construct Hodge cycles in Griffith form, right? But I would like to know, in fact, the Griffith form in order to compute the associated Artin-Gorenstein idea, right? This is my goal, right? My goal is trying to compute this idea, but it turns out that computing this ideal in general is simpler, it's easier than computing the Griffith form of the cycle lambda. And so the problem of knowing if this class is rational or not can be detected just in terms of this ideal, not passing through the polynomial defining the Griffith form. And well, there is a positive answer, a very partial positive answer in a very particular case that is given by an argument of Poisson, and it goes as follows. So we can consider the formations of X. So we can look at the Fn/2 locus. So what is this? It's exactly this. T will be the parameter space of whole smooth degree D hypersurface of a fixed projective space. And inside this space, we can look at the deformation of the class lambda, right? By deformation, I mean the monodromy. So we will look at the locus of deformation where the deformed cycle is still in the middle part of the Hodge filtration of the deformed hypersurface, right? This will give us an analytic subvariety of the whole parameter space. And what we can do now is to keep track of the Hilbert function of this associated Artin-Gorenstein ideal, but looking at the Hilbert function along the deformation, along this Fn/2 locus. And so what it happens under certain conditions on the possible values of the Hilbert function of this class is that the function remains constant, so it is continuous if and only if the original class is Hodge. Right? This is what is happening. And in fact, it is enough that it will be constant for the smallest degrees generate or smallest degrees of this ideal. So, well, this is due to the fact that, as I explained before, this ideal is containing the equations supporting the algebraic cycle, supporting the Hodge class, right? And so, whenever the deformation is keeping track of the algebraic cycle, meaning that there is an algebraic deformation of the algebraic cycle inside this family, and the equations of these cycles are not collapsing. They are not. They will be preserved along the deformation, right? So this is what we expect to happen. So in view of variation of Hodge conjecture, which claims that whenever we take an algebraic cycle and deform it inside this Sn/2 locus, it will always be supporting an algebraic cycle obtained as the formation of the corresponding cycle, the original corresponding cycle. Well, what should be easier to prove is the following question, right? Consider now an algebraic deformation of an algebraic cycle and look at the Hilbert function of the corresponding class of the algebraic cycle along the deformation. So the Hilbert function should be constant, or at least constant in some smaller degrees, or the degrees generating the equations of the corresponding algebraic cycle inside the hypersurface. So, well, for me, this should be implied by these two facts, right? The fact that if this is true, right, if this fact that the Hodge cycles or the Hodge condition is characterized by the continuity of the Hilbert function of this along the deformation, and also in view of variation of Hodge conjecture, this should be true. But this seems to be a much easier statement to prove. What should be, in fact, a striking result, in my opinion, is to prove this, but for every Hodge cycle. I mean, this will be a very, very strong result in the direction of variation of Hodge conjecture, or even in the direction of Hodge conjecture for hypersurface. So, well, this was more or less all the ideas that I had to talk you about. So, thank you for listening.
Thank you, Roberto. So are there questions for Roberto? So just a naive question. So you've looked at these ideas for Fermat hypersurfaces, or are there other special classes of hypersurfaces for which you have tried this?
I mean, we can. I work with them like theoretically. So, for instance, in the case of complete intersection cycles, or in this case of the twisted cubic, and in general of some determinantal cycles, we can do this. Just these counts can be done theoretically, right? Not just looking at the Fermat variety, but for instance, when you try to look for combinations or something more complicated, I believe that you have to fix an example, and yes, our preferred example is Fermat, because, well, I think it's the simplest one, just because of the Jacobian ideal is too simple, right? In this case. But I believe that this can be done in other contexts, right? I mean, not just the hypersurface of the projective space. There is some there is some people that have been developing tools for working this variation of Hodge conjecture type problems in the case of hypersurface of toric variety, and looking at their work, I believe that all these things can be also worked out in other cases. For instance, Fermat variety in weighted projective spaces, and they will also be, I believe, workable. But yes, all of this is very concrete, very computational. We have to do the counts in every particular case.
Thank you. So are there more questions? So if not, let's thank Roberto again for this beautiful talk. So this is it for today, and we come back next week at the same time.